we have seen that if we have a collection say x alpha, tau alpha, in general alpha belongs to some arbitrary index set, it need not be countable, and x alpha tau alpha is such that each x alpha tau alpha is connected then the product space, this is connected imply the product space by x alpha belongs to the index set J with product topology say tau, where tau is the product topology on this Cartesian product is a connected space, is connected. Though we have seen the proof by taking J equal to the set of natural numbers, essentially the proof is same for an arbitrary case, that means we just fix an element say A which is of the type A alpha belongs to J, then exactly similar to say x of 1 to n, here if we have alpha 1, alpha 2, alpha n belongs to the index set J, then we define x alpha 1, x alpha 2, x alpha n as it is similar to saying that if it is countable, if it is x of say if it is x of 1, 2, n, when our index set is set of natural number, we would have written this as x1 cross x2 cross xn, then a n plus 1 cross a n plus 2, this means they are singleton cross etc. Then this space consider as a subspace of pi of xn n1 to infinity, and we have seen that there is a continuous function from x1 cross x2 cross xn to this space A y which is on to, and first we prove that the Cartesian product by induction, if x1 is connected we prove that x1 cross x2 connected, then using induction we need to prove that this Cartesian product is connected. So exactly same way here our space will be set of all x equal to x alpha, alpha belongs to our index set J such that x alpha belongs to capital X alpha, but alpha not equal to when this is for x alpha equal to belongs to capital X alpha, say in particular x alpha I belongs to x alpha I when I varies from 1 to n, for I belongs to 1 to n, so I 1 to n, and when this x alpha equal to the fixed A alpha when alpha not equal to alpha 1, alpha 2, alpha n. Then this subspace is connected, then again using this we will define y equal to union of such x alpha 1 up to x alpha n, alpha 1, alpha 2, alpha n varies from j. And this each is connected, and we will prove that it has a common point, that is if we take any element here for alpha 1th coordinate, we will have it is a this set is a containing A, and we will prove that this intersection, that is this is a collection of connected set and with the intersection non-empty, then exactly the previous case y is connected, y is connected subspace of the product space, connected subspace of the product space phi x alpha alpha belongs to J. Now it is easy to exactly in the similar way we can prove that the closure will be equal to the whole space, and we have seen that y connected imply the closure is connected, the closure equal to our product space. So hence the product space is connected. So in particular, if our index set is n, consider J equal to set of natural numbers, and each n x n equal to r for n belongs to capital N. This what we have denoted by this case, the product space phi x n, n varies from 1 to infinity. This is nothing but pi r n, either we call it x n equal to r. So we write in r cross r cross r cross etc., which we call it r power omega. We know that r is r the set of real numbers with usual topology is connected. We know that r is connected. So our coordinate space is here x n, which is r, is connected. Hence the product space, r power omega means with product topology. The topology tau is product topology on r power omega, hence the product space is connected. Now let us see that what will happen if we consider box topology on the same set r cross r cross r cross dot dot. That is, let us consider the space r power omega with the box topology. So now we have, now consider r power omega with say tau suffix B where tau suffix B is the box topology on r power omega. So, we have seen that, so in fact the function, if we define f from r to r power omega with box topology, even such a nice function f of t which is equal to t comma t comma t is not a continuous function with respect to box topology. In fact, while proving that, we have seen that the open set, because in r power omega with box topology we have the freedom -1 say comma 1 a open set in R. So, cross minus half comma half a open set in R. So, if we consider open sets of the type, the nth place component open interval minus 1 by n to 1 by n. So, this is open in R with box topology. See, in fact, this inverse image is not open in R for this function. In fact, this is not a open set in R power omega with product topology. So, in fact, we are now let us consider this open set. This will help us to see that the set, if we take the set A, consider the collection of all sequence, I mean an element here in R power omega is a sequence. So, x n varies from 1 to infinity, but we will assume that it is a not just any sequence, it is a special type of sequence, namely x n is bounded, such that the sequence x n n1 to infinity is a bounded sequence, a bounded sequence. So, we know that what is mean by x n is bounded mean sequence of real number x n bounded if and only if there exists some alpha greater than 0 such that modulus of x n is less than alpha for all n. In fact, it does not matter when we write less than alpha or less than or equal to. So, this means we have consider the real line, alpha is positive. So, minus alpha here plus alpha, all the x n's will lies in this open interval. So, then we say that is x n is bounded. In fact, it is inside some open sphere or in this case open interval. So, if you analyze this bounded sequence with respect to this open set. See, now let us fix a bounded, I mean an element of this set of all bounded sequences. So, the capital A, in fact, in the usual analysis class we use this as L suffix infinity with a suitable distance function. So, for us this is just a set which contain the set of all bounded sequences. Now, fix, so let us fix, let say A equal to say A suffix n 1 to infinity, this belongs to the set A, that is A is a bounded sequence, that is A is a, this we write for bounded, A is a bounded sequence in R. So, this is, that is, hence there exists some alpha greater than 0 such that modulus of A n is strictly less than alpha for all n. So, now consider this open set which is open in the box topology. So, if we consider any element, say our open set U is open interval minus 1 comma 1 cross minus 1 by 2 comma 1 by 2 cross etc. So, open interval nth place, open interval minus 1 by n to 1 by n cross etc. So, if we take an element say x which is a sequence xn belongs to U. So, hence each xn the nth term will be in the open interval minus 1 by n to plus 1 by n. So, then xn, then we will have, then for each n xn belongs to open interval minus 1 by n to plus 1 by n. So, this means xn and here. So, in fact this is, if we consider this is a open set containing the origin, so 0 comma 0 comma 0. So, now just we translate instead of this open set, now we consider the open interval, with this we will just add a n. Now consider an open set now containing the set A, not just containing the origin. So, we will just translate, consider the sender is, so here see mod x. So, we will consider the open set mod x1, consider say open set V. Now, open interval say a1 minus 1 to a1 plus 1 cross a2 minus half comma a2 plus 1 by 2 cross nth place an minus 1 by n comma an plus 1 by n cross etc. So, this is our open set containing, see now A is an, the nth interval, this is a open interval, sender at an See, the center is a n and radius is 1 by n, a n minus 1 by n, a n plus 1 by n. So, now you take any element in V. So, we have fixed this is an open set, in R power omega with box topology. So, open set in R power omega containing the point A, containing A. Now, what will happen if we take an element in V? So, now if we fix any x, let us say let x equal to say x n belongs to our open set V. So, this that means the nth term, then x n belongs to the open interval center at a n and radius 1 by n. So, a n minus 1 by n to a n plus 1 by n. That means that is, then this implies, then hence we have the distance between, so that we call it mod x n minus a n is less than 1 by n. In fact, when n tends to infinity, this goes to 0. I mean, even without knowing convergence, intuitively we feel that this x n and a n they come closer. So, we will use this idea to prove that once if we assume that a n is a bounded sequence, then every element in V is also a bounded sequence. So, that is, now we want to prove that x n belongs to V, and then that claim x n, the sequence x n is a bounded sequence. That means x belongs to V implies x will belongs to the set A. See, now I mean, which is almost trivial. So, I consider mod x n. So, now we can add and subtract a n, mod x n minus a n. So, plus a n, just we ordered 0. Now, use triangle inequality. Now, this is x n minus a n together, mod x n minus a n plus mod a n, which is mod x n minus 1 by n. In fact, it does not matter, need not be even whether less than or equal to 1 by n, or even if it is some fixed constant less than or equal to 1 by n, and mod a n is less than alpha. We have taken that A is a bounded sequence, hence mod a n is less than alpha for all n. So, hence this will be say less than or equal to 1, 1 by n is less than or equal to 1, 1 plus alpha. Now, that is we have mod x n is less than or equal to 1 plus alpha for all n. So, that implies this x n is a bounded sequence. So, that is what we have proved is, hence x belongs to, that is we have proved that x is in V implies x is a bounded sequence, that means x is in A. that means what? The neighborhood V is completely contained in A. This gives that, this implies V is a subset of A. So, we started with an element A and we got a open set V open set containing the point A, and that open set is completely contained in A. That means that point A is an interior point of A. Say so hence we have proved that if we start with a bounded sequence, that means A belongs to capital A we started, that imply A belongs to A interior. So, that will imply A is a subset of A interior, but always A interior is subset of A. So, that implies A equal to A interior. This implies A is an open set. So, in fact exactly the same way we can prove that not only A, even the complement. So, what is the complement of A is the set of all sequences which are not bounded. So, such sequences we call it unbounded, that is from r power omega we remove the set A. So, this we call it complement of A with respect to r power omega. So, now we can prove that even this set is also open. See, in fact the idea is same, consider the same neighborhood. So, now let us fix, will if you, so again we will use the same notation. So, take say A which is equal to a sequence A n 1 to infinity, now belongs to not in A but in the complement. It does not matter, now first part of the proof is over. So, this A is fixed and from the complement of A, that means A is not a bounded sequence. So, that means this sequence A n is not bounded. So, now in this case here also, so see that let us see the relation between the neighborhood, the open set between V, again we are using the same notation V. So, instead of using the, we will use the product notation, say pi open interval. So, center is A n minus 1 by n, A n plus 1 by n. So, we have this n 1 to infinity. This is same as writing when n equal to 1, A 1 minus 1 comma the open interval, A 1 minus 1 comma A 1 plus 1 cross A 2 minus half to A 2 plus half and so on, cross dot dot. So, the same notation. Now, only difference now here, this sequence A n is not bounded, it is an unbounded sequence. So, if an element in, if we take an element x in V, after some stage that xn will come closer to an. So, that means the same property will be satisfied, xn come closer to an, hence an is not bounded, imply that element in V are also not bounded. So, let us formally see how we can prove this statement. So, again our claim here is, claim is the V. Now, our V is again the same, each basic open set is here, the nth coordinate is an interval. So, claim this V is a open set containing A, because an is here. So, A equal to an belongs to V. So, V is a open set containing A, and will prove that this is contained in r power omega difference A, meaning is every element of V is a sequence, and that sequence is not a bounded sequence. So, here will, in fact, let us proceed by contradiction. What will happen? Suppose, that means there exists an element, suppose there exists an element, say there exists element means here it is a sequence, x equal to xn belongs to V, but that element xn is not in the complement r power omega difference A, not in A complement, but xn does not belongs to complement of the set A. This is what our A complement. That means what? Xn belongs to capital A. Then that is, this means that, then this means the sequence xn belongs to A, that is xn is a bounded sequence. This is bounded sequence. So, xn is a bounded sequence, hence like previous case, hence there exists, okay, here we will use some other notation, hence there exists a constant, say lambda greater than 0, such that modulus of xn is less than lambda for all n belongs to capital N. See, that is it. Now, xn and an they are closer. So, this that will prove that the sequence an, now this sequence is bounded, will imply A will be bounded. Now, consider again an. So, just we will change the role here in place of an, now consider xn. So, now add and subtract xn, that means an minus 0, that means minus xn plus xn. Again triangle inequality, less than or equal to mod an minus xn plus mod xn and because our sequence xn belongs to V, we have xn is in V, that means mod an minus xn will be less than 1 by n, and n is say that mod xn less than lambda, that means this is less than or equal to 1 plus lambda, lambda is positive fixed, that means 1 minus lambda is our constant, that is mod an is less than or equal to 1 plus lambda, which is a constant. This is true for all n. This implies an is a bounded sequence, but whereas an is in A complement, means it is not a bounded sequence, which is a contradiction. That is, if we assume that there is at least one element in V which is not in A, then we get a contradiction. Hence, every element in V is in the A complement. So, hence what we have got is, so hence we have proved that this gives that this contradiction, that is this imply an is a bounded sequence, that imply A equal to an belongs to capital A contradiction. So, we arrived this contradiction if we assume that there is an element x in V, but not in A complement. So, hence what we have proved is x belongs to every element of V should be in the complement, mean VC is subset of A complement. So, hence if we start with an element in A complement, that is A, then we will get a neighborhood V containing A, that is completely contained in A complement. That means that A is an interior point of A complement. So, every point of A complement is an interior point. So, that implies A complement is also open. That means we got a separation, or in other words, the set A is both open and closed, and of course further this note that A is non-empty, which is trivial, and also A not equal to r power omega, because there are sequences like 1, 2, 3 which is not in A. So, that means A cannot be equal to r power omega. So, we have proved that this set r power omega with box topology is not connected. So, this is not connected because this set A is both open and closed, and that set is non-empty, not equal to r power omega. This set is both open and closed in the box topology in r power omega. So, that imply r power omega with box topology is not connected. So, box topology here will not behave that nicely compared to product topology. So, now we have already seen that in R intervals are connected and they are the only connected set in R. So, here we can see that, for example, if you consider the R2. So, that means we can see that the product topology induced by R with usual topology on R2 will be same as the topology induced by the metric on R2. So, metric means the Euclidean metric. So, here if you take the interval, so one interval is connected, take another interval, either it is open or semi open, closed or any interval, then the in this case for example the product. So, again you will get a open rectangle, so which will be connected. So, these are all easy to see from even intuitively. So, now let us introduce a concept called pathwise connected, and just we will leave it as an exercise to prove the related properties of connected sets and pathwise connected. Path means there is a path joining any 2 points in that space. So, we have a topological space say x tau like R2. Think of R2, a topological space x tau, a topological space x tau, this is our definition. A topological space x tau is said to be a pathwise connected topological space. So, said to be a pathwise connected, just we say that pathwise connected space means pathwise connected topological space. If and only if, again if or if and only if one and the same. If and only if, see here we have some space can be anything. So, like this is some our space Ax in R2. So, now take any xy. So, is said to be a pathwise connected space if and only if for each pair, for that means for x comma y belongs to our space X, we have taken xy in the space capital X. Now, we should be able to join them, so need not be a straight line. In fact, we do not know whether what you mean by a straight line. So, here, but we can define a curve, meaning is a continuous function with initial point x, meaning is at time 0 you are at x and at time 1 you will reach y. That means for xy belongs to x, there exists a path or an arc that is nothing but a continuous function. For each pair for xy belongs to x, there exists a continuous function, that continuous function, let us say f, that will depends upon xy. So, there exists a continuous function say f, here we are not using, it is that f depends upon xy, that is understood. There exists a continuous function say f from the closed interval 0, 1, 2, the topological space X, X means with the given topology tau, that function should be there exists a continuous function here closed 0 1, the topology here is the usual considered as a subspace of R with usual topology. This is a continuous function satisfying the condition that at the beginning you are at X. So, we have closed interval 0 1, we have a continuous function say f which takes the point 0 to X, 0 will go to X, 1 will go to Y, I mean in between we do not right now worry what will happen to the points in between, will be it will trace a curve, that is how we define a curve in a plane, mean it is just a continuous function from some closed interval or in particular 0 1 to Rn, a continuous function mean that is a curve joining the point f at 0 and f at 1. So, there exists a continuous function from f from closed 0 1 to x tau satisfying the condition that f at 0 is x, f at 1 is y. In fact, f we call it is a curve or arc joining x and y. So, that is why we are joining x and y with a curve. Then we say that the space is pathwise connected. So, this should be true for each pair x y, and the function f it will in general it depends upon x y. It means we will not get the same function naturally. So, for example, if we consider even in consider that for example, the disk in R2. So, let us say center at 0 0, radius 1. So, here if we take any point x, any y, in fact we will see that any y, this in this case it is a what is called convex, meaning is the line segment joining x and y. So, for what is our capital B, we call it set of all x which is equal to order pair x1 comma x2 belongs to R2 such that x1 square, so that is such that x1 square plus x2 square less than or equal to 1, the unit disk center is x. Now, take any x, x mean order pair x1 comma x2. So, y equal to order pair y1 comma y2. So, this we can be joined by a line. So, that is for x y belongs to this capital B, define a map, define f from where to where, we have to define from closed interval 0 1 to our space now capital B, which is a subspace of R2 as f of t equal to 1 minus t, the initial point x plus t times y. So, here what do you mean by t of y, mean order pair y1 y2, where we define this the usual way t y1 comma t y2, scalar multiplication we say. So, under this we define the map x y fix t varies. So, we can easily prove that this is continuous and f at 0, when t is 0 we will get x and t is 1 this is y, here it is 0 you will get y. So, that is a path joining for any 2 point x y. So, that means this will be connected, that disk, and we know that continuous image of connected set is connected. Then we will see that, I mean we may not have time to prove everything, like pathwise connected implies connected, but if a set y is a open subset of Rn or in particular say R2, then every connected set is also pathwise connected, that is if y is open and y is connected then it is pathwise connected. So, let us see the remaining thing in the next class.